that the first airline's flight is fully booked on a particular day, and F is the event that the second airline's flight is fully booked on the same day. Let the probability of A be 0.7, the probability of F be 0.6, and the John probability EF is 0.54. Now you need to find the conditional probability of E given F and the conditional probability of F given E. Can you tell me the answer quickly? 0.9, and the other one is 0.7714. That's correct. Okay, let's go through the question. The same, good.
Of E given F, okay, and we knew that it is in fact the ratio between the John probability EF and the unconditional probability of F, okay, and this becomes 0.54 for the John probability over here, and this is 0.6 for the probability of F. Therefore, you get 0.9. Okay. Second, you want to find the conditional probability of F given E. So you get the John probability of FE, which is the same as EF, divided by the probability of E. Okay. And this is 0.54 divided by 0.7. So after that, you get something like 0.77 that you got. I think exactly the same value, 1.4. Okay. Is any question? Is it all clear? All right. Let's try the next example. Approximately 30% of the calls to an airline reservation phone line result in a reservation being made. Suppose that an operator handles 10 calls. What is the probability that none of the 10 calls result in a reservation? And what assumption did you make to calculate the probability in the first question? What do you think? Well, let's talk about the assumption first. If you have 10 calls and you want to calculate the corresponding probability, you need the assumption that all the calls are independent. Okay? If you don't have the assumption of independence, you cannot calculate the probability. So you need the assumption of independence. Okay, good. How about question A? You want to find that the probability that none of 10 calls result in a reservation. It means that you want to find the probability that the first call results in a reservation, and the second call results in a reservation, and the third call results in a reservation, and so on. Okay, up to the 10th call. First, you need to use your university account to join the meeting. Okay. All right. So now you get because all the calls are dependent, this becomes the probability that the first call results in a reservation times the probability that the second call results in a reservation, and so on. Okay, that makes sense. And the probability that I'm sorry, I think I need to change a little bit. Not the call, so this should be doesn't. Okay, does not, and this means does not, and the third call does not result in a reservation, and so on. Okay, so the probability that one call results in a reservation is 30%. Okay, therefore the probability that a call does not result in a reservation should be 1 minus, right? So you get 1 minus 0.3 for the first, 1 minus 0.3 for the second, and so on. And then you get 1 minus 0.3. So after all, you get 1 minus 0.3 to the 10. All right. Well, if you want to give a brief solution, then you should say it this way. Well, let EI be the event that the ith call does not result in a reservation. Then the probability that you need to compute is the probability that E1 times E2 times En, and you get the probability of E1 times the probability of E2 times the probability of En. In this case, you have 10, right? So you have E10. And after all, you get 1 minus 0.3 times 0.3 and so on. So you get 1 minus 0.3 to the 10. Understand? All right. Is that a question? That is question A. Next, what is the probability that at least one call results in a reservation being made? Now, suppose that A is the event that none of the 10 calls results in a reservation. So suppose that A is the event that none of the 10 calls results in a reservation, and we denote it by A. And I denote it by B, the events that at least one call results in a reservation being made. I denote this one by B. Okay. Then the probability of B is 1 minus the probability of A. Okay, where the probability of A is the one that you already obtained. So the answer will be 1 minus 0.3 to 10. Is that okay? Good. Any question at all? I see that some of you already got the answer. Very good. And it should be, let me check, 0.9718. You need to round a number. All right. Okay. The next question. Is that all clear? Is it good? Okay. Great. Question 3. Consider the summary data for the men who participated in a study. Then you have the following table. find the probability of A of S, the probability of S given A, the probability of S given B, and tell me which treatment appears to be better. Please type in your answer in the chat window. What do you get? What is that? Anyone got the answer? Any luck? What is the probability of S? Please type in your um, your answer in the text box. Okay, so you got the answer 0.6. So A is better. Okay, so I'm going to compute the total number of patients, which is 240. Okay, and the probability of S is 140. This value 140 divided by 240. Okay, which is 0.5833. Okay, that is the first one. How about the conditional probability of S given A? This is the conditional probability of the joint probability SA divided by the probability of A. Okay, which is the joint probability is 120 divided by 240. All right. The size of the sample space is still 240. It is fixed. The probability of A is equals to 200 divided by 240. And you get 0.5. Sorry, no, it should be 0.6. Okay. There is another way to compute the conditional probability of S given A. The conditional probability of S given A is the probability of S when you knew the fact that A already occurred, or let's say you want to find the probability that a patient survive if the patient received treatment A. Therefore, you only need to focus on this row corresponding to treatment A, okay? And you see that the probability that a patient survives should be 120 divided by 200. So you get 120 divided by 200. And you should get exactly the same value, 0.6. Okay? They are the same. Alright, how about the conditional probability of S given B? It is given B. So it should be 20 divided by 40. Alright? So you get 20 divided by 40. And you get 0.5. Alright. Based on these two probabilities, you can conclude that treatment A is better because if a patient receives treatment A, his chance to survive is 60%. While if the patient receives treatment B, the chance to survive is only 50%. Okay, that's why A is better. And all of you got the correct answer. Very good. Is there any question? Okay, thank you. Now I want to talk a little bit more about this data. I'm going to copy and put it over here. All right. Now you have this table, and we already compute the probability of S given A. It is the probability that the probability of S given A. Okay. How about the probability of S and A, or the probability of S or A? S or A is the probability of S plus A. S and A is the probability of S times A. Understand? Okay. We already did the first part. Now I want to talk about the probability of S and A. It is the John probability, and we knew that that the answer is 120 divided by 240. So you get 120 divided by 240. Okay, it is 0.5. How about the probability? How about the probability of S plus A? In order to do that, you have to use you have to use A. You have to use A, and you have to use S as well. Correct? You have three numbers to get: 20, 120, 80. Therefore, the probability should be 120 plus 20 plus 80, all divided by 240. Okay? Is there any question? Good. Another question. The probability of either S or A? Either the patient received treatment A or he or she survives. What is that probability? In this case, you need to omit the John probability. Okay, we need to omit the John probability. We don't have that. Makes sense. And the answer will be 20 plus 80 divided by 240. So you get 20 plus 80 divided by 240. And you need to omit the John probability 120 over 240 in the answer. Is there any question about it? Is that all clear? Question 4. A recreational equipment supplier finds that among orders that include tents, 40% also include sleeping mats. Only 5% of orders that do not include tents do include sleeping mats. 20% of orders include tents. Determine the following probabilities. The probability that the order includes sleeping mats. The probability that the order includes a tent, given that it includes sleeping mats. In this problem, there are some events. This is one event, okay, and this is another event. The order equals to 10, and I will denote by S the events that the order includes sleeping mats, and I will denote by T the events that the order equals a tent. In question A, you want to find the probability of S. I got the answer 0.13 perhaps for the first question and 0.615 for the second. Very good. Let's give it a try. Now you have several numbers, right? You have numbers 40%, 5%, and 20%. Okay, what are they? You see that first of all, 20% is the probability that the orders include 10, so it should be the probability of T. Okay, so if you have no information about the order, then the probability that it equals to 10 is 20%. How about the probability? How about 40%? 40%. What is that? 40% is the probability that an order includes sleeping mats. Among orders that include 10. So given the fact that it equals 10, right? So if an order includes a tent, then the probability that it also includes a sleeping mat is 40%. Similarly, 5% is the probability of S given T bar. If an order does not include a tent, then the probability that it includes a sleeping mat is only 5%. Okay. Now I'm going to construct a probability tree to describe the problem. So you get T here and then T bar. Okay. The probability that you have a tent is 20% and 0.8 for T bar. And if an order equals a tent, then the probability that it also equals a sleeping mat is 40%. And the probability that it does not equal a sleeping mat is 50%. If an order does not include a tent, then the probability that it includes a sleeping mat is 5%. And the probability that it does not include a sleeping mat is 95%. That makes sense to you? Good. Now I'm going to use this one. The whole thing is to compute the probability of x, which is the probability that the order includes sleeping mats. So question A, you want to find the probability of s. Well, you have two s, you get this s, and you have another s. Okay, so you want to find the probability that you observe s. The probability that the first scenario occurs, this scenario occurs, is 0.4 times 0.2. Okay, and for the second scenario, you get 0.05 times 0.8. That makes sense? And the probability of s should be the probability of s given t times the probability of t plus the conditional probability of s given t bar times the probability of t bar. So s given t is 0.4 times 0.2, which is the first expression you got. And for the second term, you get 0.05 times 0.8. And after all, you get 0.08 plus 0.04, which is 0.5. Is that okay? Oh, you cannot see which part of the screen. Part that better? Do you understand the solution? Okay, good. Oh, you cannot see the screen? Which part? Oh, I see. Perhaps because of the network. Okay, let me try to stop and then and share the window again. Next part, the probability that the order includes a tent given it includes a mat. So you want to find the probability. You want to find the probability of t given s. Whenever you see the word given or if or provided that, then you should think of conditional probability. Okay, I want to find the conditional probability of t given s. Okay, it means that we knew s already occurs, and you want to find the probability of t. Okay, so you want to find the probability that the first scenario occurs, not the second. Okay, and you come up with the probability of s given t times the probability of t divided by the probability of basically s. The probability of s. The probability of s is 0.12. It is 0.12.
Okay. How about probability of S given T times the probability of T? It's the first term of the probability of S. Therefore, you get 0.4 times 0.2 for the numerator. And after all, you get 0.08 divided by 0.12, which is 2/3. Oh, you cannot see the screen. Is it okay now, or is it still frozen? Oh yes, I did. I gave you the solution the second part. I don't know. Let me stop and share this window again. Okay. Because I already gave you the solution of the second part. Do you see that? Do you see the probability of t given s? Okay, so that's I gave you. Good. I think it's better now. So is there any question about that? You understand the first part, probability of s. Second, the probability of t given s. Do you have a question about them? All clear. Okay, very good. Next, question 6. An electrical system consists of 3 components as illustrated in the figure. The reliability of each component is also shown in the figure. Find the probability that the entire system works. B. Find the probability that component A works, given that the entire system works properly. We have the assumption of the independence of all components. E, okay, E is the event that the first part works properly. F is the event that the second part works properly. So this is F. Understand? And I will denote by S the event that the entire system works properly. Now I want to find the probability of S.